This session, we will focus on Anaqsim's unique version of the analytic element method, which makes use of subdomains as opposed to infinite unbounded domains, and it also makes use of spatially variable area sinks. These two things, combined in the way they are in Anaqsim, give it much more capability than other AEM programs. It's possible with Anaqsim to simulate multi-layer 3D systems, and it's also possible to have fully transient simulations with lots of different transient features in them. We'll look a bit at Anaqsim's AEM, how that leads to computational efficiency, and some comparisons with other AEM programs, and finally some checks against analytic solutions and a numerical model. Before talking about Anaqsim and how it is different than other AEM programs, I'll outline what has been typical for other AEM programs. Each layer in a model, if it is multi-layer or if it's single layer, is unbounded and infinite. There's no external boundary to the thing. It just goes off to infinity, and all elements in the model are internal to this infinite domain. And all other programs that I know of had isotropic hydraulic conductivity in the plane of flow, and each layer is just one mathematical model for potential head discharge, and every element in that layer contributes to those equations. When you want heterogeneity, they typically have been called inhomogeneities by earlier AEM programs, and these are closed curves or polygons that are internal to the infinite domain, and they separate two regions with differing properties. And in a single layer model, the system of equations creates a fully populated n by n matrix where n is the number of equations, and there are no zero coefficients because every element affects every other element in the plane. And some of the examples of these programs include Otto Strock's programs, MLAEM, SLAEM, my earlier program Tudan, Hank Heichema's program GFlow, among others. Anaqsim's implementation of the AEM is a bit different. It uses what I call the subdomain concept, and in each level, the model is not infinite, it's bounded. There's a lateral external boundary to the thing, and each layer can be divided into separate subdomains, which I'll just use the word domains to be economical. And each domain has its own hydraulic properties, its own elements, and its own mathematical model that is distinct for each domain in the layer. So there can be multiple mathematical models. The user doesn't really see that because they see it as a whole layer, but there are separate and different mathematical models for each domain. And each domain may be anisotropic with a unique direction and ratio that even within the same layer can vary from one domain to another. And a domain's model has contributions only from elements that are internal to it or on its external boundary. And the system of equations that results is going to have a lot of coefficients that are zero. For example, where an element in domain A is not going to factor into the equations for domain B and vice versa. So that builds in a little bit of computational efficiency. The domain boundaries in Anaqsim can be a variety of different types of external boundaries, either head specified or head dependent flux or interdomain between two domains. So they can be external boundaries or within the internal part of a model. And within a layer in Anaqsim, the domains you have can be varied. In one part of the layer, it might be confined. In another part, it might be unconfined. And in a third area, it might be a fresh salt interface area. This is a bird's eye view of an Anaqsim model with just one layer, and it has three domains. This blue one, the yellow one, and the green one. And there are different kinds of external line boundaries that define the external limits of each domain. This green boundary I'm tracing here is an interdomain boundary, hence ID, that separates the green from the yellow. This is another interdomain boundary that separates the yellow from the blue. There are other kinds of boundaries here. There's a normal flux specified boundary here, another piece of one here, another piece of one here, a head specified boundary out here, and another out here. So the boundary of this yellow domain, for example, has quite a few different stretches that are different kinds of boundary conditions. So unlike other AEM programs where each inhomogeneity had to have something akin to this interdomain boundary encircling it, in Anaqsim you can have a variety of different boundary conditions, including external ones and internal ones. This shows conceptually what Anaqsim is doing under the hood when you have three domains in a layer. The heavy dark lines are external line boundaries between these three domains. The dotted lines are internal line boundaries, and we have a few wells, 2 wells here. In Anaqsim, it's actually 3 distinct separate models, and I've pulled these apart in the right-hand side so that you can envision what each model is like. Where we have an interdomain boundary, there's actually a line boundary in the yellow domains model along that stretch, and there's also a line boundary along the blue domains stretch that corresponds to that. And the conditions along those boundaries that get met or approximated are continuity of head and continuity of the normal component of discharge. So that just illustrates how Anaqsim actually has 3 separate models here. And anything internal to the yellow model, for example, or in the yellow model, doesn't directly influence anything in the blue or green models. With the older other versions of AEM, with the infinite domains, there had to be a boundary condition that determined how much flow is going to or from infinity. And that was generally achieved using something that Strzok called the reference head. You just pick a point out towards infinity, somewhere finite, and set the head there. And that in turn would determine the gradients from your modeled area of interest towards infinity. And in the years that I had my 2DAN program, which also had a reference point, an infinite domain boundary condition like that, I found a lot of users were quite confused by that. They didn't really understand that there was this one equation that was going to determine how much water came to or from infinity. And instead, with Anaqsim, there is no infinite boundary, just the finite boundary conditions at the model's outer limits. And that I think is a lot more intuitive. You can set it to be a fixed head in this one region or a no flow boundary in another, and that all accords a little more reasonably with what happens in nature. In Anaqsim and in almost every other AEM modeling software that's available, the models are 2-dimensional within each domain. And that is achieved by neglecting the vertical resistance to flow. So you're accounting only for the horizontal resistance to flow within the domain itself. And when you neglect the resistance to vertical flow, there are no vertical gradients perpendicular to the plane of the model. And the heads and the specific discharges are independent of elevation. This is illustrated in these 2 sketches down below here, where on the left, this is the actual situation, and the dotted lines are contours of equal head. So this is a vertical slice. So the heads change with elevation. In this case, there's a bit of recharge coming in the top, driving a component of downward flow, which creates a downward hydraulic gradient. The Dupuy model, which is what you get when you neglect the resistance to vertical flow, looks similar. There still is vertical flow going on. It's just you're not attributing any resistance to that vertical component of flow. As a result, the head contours are vertical, and at any one x, y location within your 2D plane, head is independent of elevation, and so is specific discharge. We get to three-dimensional modeling by stacking multiple domains and accounting for the resistance of flow between them. That's how Anaqsim does it. The three-dimensional and transient capabilities of Anaqsim are achieved using spatially variable area sinks, SVAS, which distribute discharge over areas and do it in a way that is spatially variable. In other words, the rate of discharge per area varies with location, and it's spatially variable. And that allows you to have, for example, higher rates of vertical leakage near a partially penetrating well, also higher rates of storage flux near a well, things like that. So these distributed source sink discharges are due to two potential phenomena in a model: vertical leakage between layers in a multi-layer model, and fluxes in or out of storage due to transient stresses. And the vertical leakages are computed using typical Darcy's law, head differences between two levels that are adjacent, and you assume that the head in a domain applies at the center line of the saturated thickness, and you're computing head difference and vertical conductivities for the intervening materials. Say you have layer 1 and layer 2 below it, you'd use the lower half of layer 1, its vertical conductivity and thickness, and the upper half of layer 2, its vertical conductivity and thickness, to compute the vertical leakages. The storage fluxes are computed using finite difference time steps in a transient simulation. So it's a backwards time step. You use the head at the previous time step, the difference between that and the head you're computing at the current time step, and then multiply that times storage factor in a typical fashion. Anaqsim's subdomain approach allows layering schemes that were really not possible with other modeling programs. You can have more layers in the area of interest and fewer layers or a single layer in the far field. The far field is often less important to the questions you're trying to answer, and there's often less data available there, so reducing the complexity out there makes sense. And it's smart because you don't spend a lot of computational effort in areas where you don't know much or where it really doesn't matter that much. Here are two vertical profiles to illustrate some of the possibilities with layering schemes. This upper one, we have a single layer in the far field, this pink zone, and it is joined to a three-layer area in the center by an inner domain boundary here. And this inner domain boundary can have any number of domains on one side and a different number on the other side. What is equated at the inner domain boundaries is head at control points and the normal component of discharge total. The sum of the normal component of discharge from these three levels must equal the normal component of discharge on the single level side. In this scheme here, there's also an inner domain boundary here to allow a different domain with different properties, possibly different elevations, in the blue area compared to the green. This lower example is similar, except that in the middle part, each of the three layers here, the green, yellow, and orange, have been split using another inner domain boundary into two. So this bottom layer becomes levels 5 and 6 in the innermost zone, and so on up the line. These are different inner domain boundaries with different colors. that make those transitions. This could be handy, for example, if you had a partially penetrating well that was screened where levels 4 and 5 are, and you wanted a lot of detail right around that partially penetrating well. This slide shows conceptually the difference between the infinite domain AEM approach and Anaqsim's finite subdomain approach with respect to the system of equations that gets built. The entire system of equations is what's bounded by this black box. On the left, the infinite domain AEM, every coefficient in the matrix is non-zero, and thus non-zero ones are shown green, and that is because every element impacts every other element. So there's connection between every boundary condition and every element in the traditional infinite domain, single domain AEM. On the right is the mock-up for an Anaqsim model with 3 subdomains. The 3 big blocks here that are all green with non-zero coefficients represent the equations and coefficients for internal boundary conditions. So, for example, all of these rows from here down to here are boundary condition equations for control points or intervals in the first domain. And then this block from here to here, these are equations for the second domain. And from here down to here are equations for the third domain. And these solid blocks represent boundary conditions, say, within domain 1, and their impact at other boundary condition locations within domain 1. These scattered non-zero coefficients, represented by these green speckles out here, represent boundary condition equations or coefficients where the equation involves not only something internal to, say, domain 1, but something external to domain 1 in one of the other 2 domains. And there are 2 kinds of equations that can do that basically link up the subdomains to each other. One are interdomain boundaries, which are for laterally abutting domains, and those generate equations for continuity of head and continuity of discharge across those domain boundaries. The second are SVAS, spatially variable area sink equations that involve vertical leakage between stacked domains, between one domain and the domain that overlies it, for example. So I was curious about just how sparse an Anaqsim matrix might be, and I looked at, and I programmed a routine that would count the number of coefficients that were non-zero and the ones that were 0 and give me the ratio of those 2 things. And I found that for moderately complex models that the amount of non-zero coefficients could be less than half. And it really depends how many domains you have and how finely you've broken the entire model up into subdomains. If you do a lot of that and break it into numerous small subdomains, then you'll have more zero coefficients, more white space here. And that leads to efficiency computationally in 2 ways. One is when you're evaluating the head or the discharge or the velocity at a point within a subdomain, it's only making use of elements that are internal to that subdomain or on its external boundary. So it only uses that many equations, say, for this domain, and that many equations for this domain, and so on. So that's one efficiency. And the other efficiency is that when you're solving the system of equations, that works quicker when a lot of the coefficients are zeros. The routines that solve don't do a multiplication by zero. They know that the product's going to be zero. So if you have zero coefficients, that helps quite a bit in areas like this. This table summarizes a comparison that I have posted on my website at this URL between Anaqsim and other AEM programs. And quite a lot of them do not do transient flow, and quite a lot of them don't do multi-level modeling as well. None of them do anisotropy, and none of them have the flexible layering that we'll talk about later in this series of videos. So you can see a little bit more detail at that link. Lastly, I'm just going to walk through a few checks of Anaqsim versus analytic solutions and other numerical models and so on, just to give you some comfort that I've done a lot of testing, and most of this can be found at the link down here. I think there are 20 plus different checks of Anaqsim posted at this link on the website, and these are a few of them. This is a check against the Tice solution. The ones that are shades of orange to red are the analytic solution of Tice, transient flow to a well. The blue shades are an Anaqsim model that's replicating that quite well. This is a check of Anaqsim against an analytic solution for transient flow into a rectangular recharge area by Hantusch in 1967. And I did hand calculations for the predicted head at one of the four corners of this barely visible green rectangular area. And the Anaqsim simulated head versus time is the blue line, and the hand calculations fall right on top of that. This is a comparison of Anaqsim versus ModFlow. It's a two-layer model with transient flow, anisotropy, and heterogeneity. And I won't go through all the details, but the Anaqsim predicted head contours are on the left here in two different layers, and the corresponding ModFlow predicted heads in two different layers are these colored lines over on this side, and you can see that they mirror each other quite well. Another kind of check that I did in a few cases was using Anaqsim in two different ways to model roughly the same thing. This is a barrier that is modeled with a skinny separate domain that has low conductivity right here. It's a rectangle. And below it is the equivalent thing modeled with a barrier, leaky barrier element that has no width. It's a line boundary. And they have equivalent resistance across the barrier, and you can see the flow fields are nearly identical. On the right, I've done the same thing with a drain. This is now a high conductivity domain inside that skinny rectangle, and below it is the equivalent drain element with the same conductance as this finite width one up here. And you can see that the head patterns are nearly identical. Here are some references you may want to delve into to learn more about the AEM. The first two are by Otto Strauch and are quite mathematical. The first of those two, the 1989 book, is thicker and more detailed than the 2017 book. Content is similar, although just pared down a bit in that one. The Heichema book is more application-oriented, less theory-oriented, covers a lot of the same ground as the Strauch books. And in my groundwater science textbooks, either the second or third editions, you will find a couple of chapters that summarize the AEM in a lot less space and a lot less detail than the references above that. And the last reference there is a paper that came out in 2010, journal article, that outlines the subdomain approach that is in Anaqsim.